White bean, go. That would be horrifying if it was that. If you just turn it off and it's like, this is my least favorite pair of binoculars. You're not gonna let it right. Why don't they spend $1,000 on this? Yeah, I ain't on that one because I thought they're real. Can you look it up?
I don't know if I had the data set.
I'll look through prototypes.
Yes.
So I will have to check.
There's other ones over there.
You can honestly just carry a camera, probably for less money.
So we need species mark.
Carry a nice camera, probably for less money.
Yep. Nice.
All right, so we have. Left off with this. I asked you to do the workup.
Yeah.
Species mark. The homework was posted, but apparently I didn't add the data files. Leave, that's CSV.
You're kind of wondering what you were doing with that.
Leave, that's CSV. It's number 3. Number 4 is tomato genotypes. So far, so good. Tomato genotypes. 4 questions? Yep, there is. Just 4 questions, right? Yes. Oh, right. Okay, yeah, maybe, maybe not. All right, so plot, CSV, check your assumptions, perform permutational Anova. So hopefully you found that assumptions were vital. Which ones? Almost everyone? Everyone? Let me see here. Get down to plaque.
Yeah, I think it was all of it.
All right, so
It was hard to tell. I think both of them were.
Yeah, the Qqq Plot were kind of hard to tell.
Definitely violated, but I'm pretty sure not many. That's well.
open it. Plaque.csv. Open strings as factors, make life easier on me. All right. Here we go. Got my plaque open. Right? So I'm going to just take a look at the plot. So we've got size as a function of compound. Data is plaque. All right. Yep, definitely. I'm going to expect a difference. Right now, I'm not going to be surprised if it's unequal variances, probably skewed. So if we go ahead and check our assumptions using Qqq Plot, size as a function of compound, data. All right, copy that. Packages. Got to make sure car is loaded. There we go. All right, so a little bit harder to see. So I will make them larger, and this is something you're going to probably have to do in the future. So we are going to do a Qqq plot, all right? But we're going to do it of a subset where we are checking the Qqq plot of size. All right, so subset returns a data frame, so that subset $size is the variable that we're doing Qqq plot of. What we want is plaque, where our compound is equal to, we'll start with P49. What I'm going to do is check my levels so that I can figure out what my numbers are. So yeah, that is a capital W, right? So I know this is gonna work, so you're gonna see me, I'm just gonna paste it twice. Focus around these. So, you get that compound W? Little humor. Right? X21-Z. All right, so first one, pretty large plot. Yeah, it looks like there's some curvature here. That's for P49. If I do W, it's a wide envelope, so we could probably get away with that one just fine. This one curves. So really the first and the last one, P49 and this X21-Z, kind of looks like it's slightly non-normal. So what I think I would do is use the Fligner test to check our equivariance assumption. And that gives me a really small sample size. So no, or at least thinking that two of these groups are non-normal or close to non-normal and are heterogeneity variances, I think I'm going to go ahead and assume that we are violating our assumption. So the next test then is our Anova. All right, and it's going to be a permutational Anova. So Anova, I'm going to go to my function script. I'm going to pull it off of here. There it is, permutational Anova. Copy it. Paste it. Update it. So our dependent variable is plaque size. Our independent variable is compound. So plaque $sign compound. All right, and I want 10,000 iterations. So when I run that, I get a small p-value, right? Small p-value. How long did it take you to run this? There it is. Right? That's the smallest value we can get. It's one. This is 1 over 10,001. That's the value. All right. So basically, we didn't see any randomized data set that generated our F statistic that matched or exceeded what we actually observed. Something other than chance is causing these differences. So the question is, well, which ones are different? So now we have to run a series of pairwise t-tests. So I'm going to get these pairwise t-tests. So this is permutational pairwise t-tests. So we're going to be running. All right. And I am going to get this first one updated. So the subset that we are running is on our plaque data frame. The variable is going to be compound. That's what we're selecting on. All right. So compound for both of these. And then we've got P49. That's one. And then the other one is W. Capital W. All right. So that created our subset. That was subdata. And then we're specifying our dependent variable, that is size. Our independent variable is compound. And I want to run 10,000 iterations. All right, so I know that's going to work. So I'm going to take this and paste it. So we've got 3 groups, right?
Yep.
So we've got, how many comparisons do we have to run? 3 total comparisons. So I'm going to paste this twice. So I've got my 3 comparisons. Now, what was that last group? X21, X21-Z, right? Capital?
Yeah.
Yep. X21 -C. All right, copy it, paste it. So I've got all three. Then I'm going to run this chunk. And while that is running, I'm going to get my p-value adjustment ready. All right, because it's going to output, should output 3 p-values. Let it run. 3 values. There it goes. All 3 values are the same. Now, these aren't values that we report because we have to adjust the p-values. So this one's pretty easy. I didn't have to go back, copy and paste. You know, copied it once, pasted it 3 times with a comma between them. That made my p-value vector. And then I adjusted the p-values. I used method as equals home to do that. So then these are the p-values that we get. And you'll see that they're the same. I mean, this is less than 0.0001, basically. All right. We would record it as less than 0.0003, but it's 10,000 iterations. So I doubt that you observed anything different with these values. Even with the randomization test being random, right, and everyone getting a different set of randomized data sets, you're probably getting these same values. Just really small, just really small p-values. All right. All right. Not bad. All right, so. All right, so I had permutational Anova. We already went through how to do this. You saw it. Here's our adjustment. Again, another time when I did that, I got the same thing. So now the writing. So I use the box plots just to make it easier. You probably would use like means with standard errors. But you can see how I reported it. So testing compounds for antibacterial activity involves growing bacteria on a plate and exposing bacteria to that compound. Formation of plaques or zones of dead bacteria reveals antibacterial properties, more potent compounds causing larger plaques. 3 experimental compounds were tested to determine the effect on E. coli. Quantile plot suggests that plaque diameters were not normally distributed and variances were not equal. So there's our Fligner test. All right, and again, you get the test statistic, degrees of freedom, p-value, and a conclusion. So as such, permutational Anova with 10,000 iterations, important to give that, let your reader know how many iterations you use, revealed that mean plaque size varied between the compounds. We don't have a test statistic, we don't have degrees of freedom. All right, we generated our own null distribution, so all that we report is our p-value. Then I say pairwise permutational Anovas, again with 10,000 iterations, were used as a post hoc test, and p-values were adjusted using Holmes' method. Compound X21Z caused the largest plaque sizes, while compound W caused the smallest plaque sizes. Average plaque size differed between all 3 compounds, so p adjusted less than 0.0001 for all comparisons. Again, this is what we found. Right? This is exactly what we found. I just kind of clarified it to specify that, yeah, they're all different, and the highest was this X21Z, the lowest was W. Does that make a huge difference? Probably not. I mean, they both are pretty effective, but it seems like X21 has a stronger antibacterial activity. All right, kind of how I work through it. That video has it. All right, any questions? All right, so violating assumptions, just kind of a summary. So which way is best? What should we do when we violate our assumptions? So generally speaking, you would probably prefer Welch's Anova if you've only violated your equal variance assumption. All right, it's easy to use, all right? Most people hear Welch's Anova and they just assume that it's a regular Anova and they don't panic about it. They see a test statistic, they see p-values, and it's like, okay, that I accept that. All right. If you get a significant difference, then you have to just go ahead and use pairwise t-test with Welch's adjustment on that. All right. I say this is preferred because there is some evidence that permutational Anova isn't really good when you have large differences in variances and small sample sizes, which it's possible, especially when you do field work. The question is, how small do our sample sizes have to be, and what kind is like our limit as far as how much of this heteroscedasticity do we allow? Good question. That's a good question. So, I wouldn't worry too much about it because you're going to probably, if you can run Welch's, just run Welch's. All right. Non-normality poses different problems. And this isn't just like statistically speaking. I mean, it takes a while to run some of these tests, especially as your sample sizes get large, but also explaining it to people, explaining why you can do this, all right, or why you ignore the assumption in the first place. All right, not everyone understands that Anova is robust to this violation. So it's one of those, that's kind of the sticking point. If you violate normality, you can kind of have to assess, well, how much of a, how badly are the data non-normal? If it's only slight, if it's, let's say, 1 out of 4 groups, you can probably ignore it and run Anova, but then you run into that issue of convincing your advisor that this is okay, or convincing a reviewer that this is okay. So in this case, I tend to suggest trying transformations first, and if those don't work, then go ahead and do the permutational Anova. Even if you have that situation where it's like, well, I can probably ignore it, my advice is just say, heck with it. Run your permutational Anova, you'll save yourself some headaches. All right, so my recommendation, if in doubt about normality and you can't transform it, go ahead and run your permutational Anova. All right. If the normality assumption is met, but data are heteroscedastic, go ahead and run Welch's Anova. All right, just go ahead and do that. And remember the post hoc test. Once you go with the permutational Anova, stick with the permutational methods for your pairwise tests. Once you use Welch's, stick with Welch's adjustment for your t-test. Now, when you run these pairwise tests, you could run into problems. Because as we increase the number of levels in our data set, we start to increase the number of comparisons that we're doing. And it can get to the point where it's virtually impossible to find the differences in our data. All right? So you get this situation where Welch's Anova gives you a p-value of less than 0.00001, but then when you run all your pairwise t-tests and you adjust your p-values, everything's above 0.05. All right? So the question is, why would that happen? Well, I use this example of Bonferroni Corrections. All right? So the critical value that we look for is 0.05. But if we were to do kind of an adjustment by hand, what we would do is set a new critical level. If we only have 5 comparisons, all right, our critical p-value that we use is 0.005, right, which has made it hard to reject the null hypothesis that our means are equal. If we increase, and that is, for 10 pairwise comparisons, that's out of 5 different groups. I don't think that's right. 5 different groups. Yeah. Yeah. So if you have 5 levels, you're doing 10 pairwise comparisons. All right. If you have 10 levels, you're doing 45 pairwise comparisons, and our critical value drops to 0.0011. All right. And you add even more, it becomes even smaller and smaller and smaller. So there could be a time where you have so many groups that you won't find significance between any of them. You're going to say, well, how do I fix that? Sometimes you just, but other times, and this is the way I would do it, is you have to be selective in how you do your comparisons. So assume we have these groups, A, B, C, D, E, F, and G, right? 7 total groups. We could do all pairwise comparisons, but it's going to be hard to detect which ones are different. So what I suggest is arrange your groups from smallest to largest, and then systematically do your comparisons. So these two you compare these two, you compare these two, all right, and then you compare this one. As soon as you find your difference, now this is, you didn't adjust your p-values. We're looking at p-values that are going to be pretty small. So like if it's 0.05 or 0.04, that's not small enough. We're looking for like the ones that are less than 0.01. Once you find that difference, then what you do is jump and do this one. If these two are different, then you know E is going to be different from all of the other ones. Because if D and E are close together, say 2 units away, well that means C and E are more than 2 units. So once you have this, we don't need to do C versus E or B versus E. That's 2 comparisons that we've just dropped. And then, so we found our breakpoint. Then what we have to do is figure out where's our next breakpoint. All right, so you compare E and F, and you compare F and G to figure out your breakpoints. But you also have to compare D and F to see, well, are they different or not? So what we're doing is just kind of systematically trying to figure out where our breakpoints are, and in the hopes that we don't have to do any of the other comparisons. Now, you can always start and look at the data as a guide to see where you start. So like if, like A, B, C, and D, if all of those means are equal, or look like the plots, the lines are pretty darn close, I would probably start here at that D to E. If there's a difference between these two, then I wouldn't even bother comparing E to the rest of these. Because I compared 2 values that were going to be closest together, and they were different. All right, and then I look at like another breakpoint. Maybe F and G was the jump. Or I do E and F and say, well, are they the same or different? And if they're equal, right, then I compare like F and G to see, okay, well, are those different? And if they are different, then I know F and G, if they're different, then G and E are definitely going to be different because of our wider span. How realistic is it that you'll encounter it? Just kind of depends on your project. All right, so I don't know if we have anyone here, but we had a student that did looked at skunks across Texas. So you have county data, and they looked at ecotypes. There's like 22 ecotypes that were in her data set, and there was a difference in ecotype. So if you did the Tukis, you didn't get a difference at all. So here's our graph. Here's our ecotypes, all right? And when you arrange them, whatever the Y measurement was, from smallest to largest ecotypes, your smallest was down here, your largest was up here, all right? And it's very clear that, yeah, they're all different, but the problem is that the data set looked something like this, and once you started doing all your pairwise comparisons, you didn't have enough power to detect the differences. So what we kind of did was say, okay, these all look similar. Let's see if there's any group there. Let's see if there's groups down here, and we kind of broke it up to say, okay, well there's this group of ecotypes that's clearly different from this type of group of ecotypes, and I think these were like similar to both, just kind of depending on what happened. But we took these, I don't know how many pairwise comparisons we had, 80 something or something like that, and reduced it down to I think 8 or 10 total comparisons. So you look at this and say, oh yeah, there's clearly a difference, but Tukis didn't tell us which ones were different. So we had to look for like an end around for it. If you run into something, chances are I'll know it, but yeah, feel free to come talk and we can work something out. All right, so here's practice number 2, fish growth. I want you to work on this here as an extra. I don't know, I didn't tell you what assumptions are violated or anything. This is kind of a prequel for our homework assignment. All right, so we've got fishgrowth.csv. Here's the idea. You have a lab population of guppies, All right, they're typically red, blue, or a combination of red, blue, and then all of a sudden you see this other mutation. All right, a white coloration or albino coloration. All right, so you already knew that there was some size differences between these strains, and you think that it's tied to pigment generation. So the different colored pigments might be more costly, or may differ in their energetic cost, which then, if you're going to produce one color, it suffers, your growth rate will suffer. So what you did was you went ahead and measured total growth after 3 months, and to see, is this growth at 3 months differed for the different colors? Go ahead and check your assumptions, perform the appropriate type of Anova, maybe permutational Anova, and then also do your post hoc test. All right? So check it out. Oops. And kind of move this briefly so we get that other slide. And I did post the fish growth onto Blackboard.
I don't know what.
Now.
Oh, there we go.
When you do the key adjust, we'll do all the values together.
Yep. Yeah, you do it all at once, because that P adjust is gonna count up to figure out how many comparisons did you actually do.
Yeah. Typically, yes.
Yeah.
worked before, but I got it.
For what?
If you do fish grill, or you get 24.
I made them a segment of this fun. That's something fun.
You know what's in my school?
Yeah.
I would rather use this
Oh, yeah, okay, yeah, I'll bring that one. What? Yeah. I'm done. Yeah.
for our practice, was like,
Yeah.
we also.
What did you write? Okay, you didn't watch this.
This
originally skip street.
Good.
If it was only homostaticity.
That I just did.
Violated the
Yeah.
normality.
Yeah.
Question.
Yeah, I was trying to I would question that.
So we use printing this out to be safe.
That's a little bit different, but I think it's about the same. Right?
Yep.
Even later
Yep.
one, that's a pretty good one, but
Yeah, when you get to
I'm not saying the same.
You did it well. Figure out how many. It's okay, I use my head.
You just do a regular 260 test? There you go. I mean, we
It's
got the
great.
same,
So,
It was pretty well now. The newer one. And things were that.
Just on the
So,
same setting.
oh, I didn't know, yeah. So that's what so you end up.
Yeah, that's what the subset is.
I did it the, one you know,
We got the same one. Yeah. That makes more sense.
So yes.
how's it going?
Everything but the write-up.
How many do I have? Yeah.
Well, you could have probably gotten away with doing the presentation. Never remember when we get to.
I was thinking that. Nope, it's not for me.
She saw R on the screen, ran the other way.
You get? Yeah. I don't have this. Me too, both right and both wrong. What do you think's more likely? I think we'll find out. Did you know that one? I mean, if you look at, if you look at the plot, they're all fairly close, maybe whatever, or not. At least one.
How's it going? Guys, not done? Ready to review it?
Let's give it a 2 more minutes.
You'll see.
Anticipation is killing me.
So here's my plot. Rendered it incorrectly. So you definitely see some differences. I'm not going to be surprised to get a small p-value. Right? Or even our whiskers don't overlap on some of these. So this looks like there's a significant difference. So then I did the Qqq plot. And again, I broke it up to do one Qqq plot per level. And you're going to see, if not today or tomorrow, today or Wednesday, but next week, you're going to see why we need to learn how to do this. So I did it based on the colors. So here's blue. All right. I see this. I've got some points outside. Kind of at the extreme. I have a large number of points here that's probably okay. Then I look at the second one. Well, this is now the second one that is giving me this curved shape where I'm outside on both of them. This one's not as bad. This one also, I see this curved shape. So I kind of think there's probably some non-normality going on. So I'm going to check with Fligner-Colleen, and I get a really small p-value. So at this point, you know, if the variances were equal, I would have probably just gone ahead and did Anova. And because again, I'm expecting a difference. All right, if I ran Anova and got a p-value of 0.06, something's not right. Something's not right based on our initial curve or initial graph. But knowing that we have unequal variances and it looks like our data are non-normal, now I'm just going to err on the side of caution and run our permutational Anova. No use trying to argue with people that it could work. So run the permutational Anova. Of course, I get a really small p-value. All right, not surprised. So then I'm left running this pairwise permutational t-test. And I ran all of them. How many comparisons? 6 of them. And this is the batch of p-values that I get. So only one had a high p-value. This right now, I need to run the adjustment just to get the p-values that I need for a write-up. So, but, I mean, all of these are super small. I know these are all different, and they stay different. All right. So only one comparison was not, and that was this blue versus the red-blue comparison. So there's no difference between these two, but then all other comparisons are different. So in the write-up, you could talk about, yeah, the white had the highest lengths, red had the lowest lengths, and the red-blue had intermediate. All right, and they weren't different. Now, the question is why? Well, that's part of the discussion then in the paper, to figure out why would this be the different. Maybe, you know, the pigment that makes that the red color is a larger pigment. Maybe there's more steps in the production of that pigment. All right. So maybe the white is just something very early on is screwed up, so you never have the expenditure of energy to get any of the later steps and so forth. So who knows? That's all part of our discussion to try to interpret the results of our data analysis. Questions?
If I ran a Welch's, how?
Welch just probably gave you the same answer,
It
right?
gave the exact same answer.
Yeah.
But would that be kind of frowned upon if you were to put it in with the Welches? Like, would they probably give it back and say, right, permutational, or?
For like a reviewer?
Yeah, for like a review.
A reviewer would probably see that and say, oh, well, if you said it was slightly non-normal, why did you proceed? That's what I said.
Yeah.
You then have to, in your rebuttal, say, this is why I proceeded. And then you might have to actually find papers that support your claim. Or the initial papers that said, yeah, it's robust.
Yeah.
All right.
So wait, Cody, did you run the lean first?
I actually ran both of them just to see what they would do, but no, I initially ran ground floor.
What was the p-value?
It was still a significant focus.
Really, what they both?
Let me try. No, they weren't that close.
I suppose that's wrong.
Yeah, the ground floor size was 0.0007. Because it's more powerful to living light, so it's going to be smaller.
It is, but it assumes normality. So that's one of those things where, yeah, the Levine test, it utilizes the median, or Brown foresight utilizes the median, which negates some of these slightly non-normal issues. So yeah, that's. All right. Any questions? All right, so I've got homework number 2. We got a series of data sets. Data actually now posted. All right, so for all the questions, you'll see it in the R markdown file. It kind of steps you through checking all the assumptions and then performing the appropriate test and the post hoc test. So know that if you get an Anova test and it's not significant, you don't need to do all of the post hoc tests. So even though in the markdown document it might have a spot for post hoc, you don't run it. So here I have it opened. So you're going to see just right from the get-go, right, you're going to have all your data and libraries. You're going to load in your datas and load in your libraries all within one chunk so that, you know, once you run it and when you knit it, it's going to run that chunk. And I also have warnings equal false. So you know how when you load car, it says, oh, this stuff will be masked from the data. That doesn't get printed. It doesn't go into your PDF. All right, so here it's like species worms, describes what the data set is. All right, check your assumptions and perform an Anova. So you're going to check your normality, homoscedasticity, run your Anova. All right, and post hoc test if applicable. All right, so if you don't get a difference in the Anova, don't run your post hoc test. Number 2, so right, I tell you to run Welch's. But again, if you don't get a difference, don't run your post hoc. Question 3 is that permutational. Question 4 is your choice. So based on everything here, you have to decide what test to run. And again, even though I say the Anova, you'll notice that I used Anova for permutational, Welch's, and all that stuff. Because our goal was to run it, but based on our assumptions that we have to choose the correct test. So question 4 is that correct test. And again, if it's not different, if you don't find a difference, don't run your post hoc. All right, so we'll do that. I'm going to ask that you work through it for Wednesday. All right, if you have questions, we get to answer them at the beginning of class. All right, this is in preparation for our exam, which will be next week.
Wednesday.
I think probably Wednesday. So we'll have class on Monday to answer any last minute questions. I believe Monday is when the application part will go live. All right, and then on Wednesday, you'll have all day Wednesday until the evening to take the closed book portion. Actually, we'll probably do the closed book portion here on. Rebecca's not going to be here probably. Darn it, Rebecca.
So we'll have regular class Monday night. And then
Yeah, we'll have regular class on Monday night, so we could answer any last minute questions. Yeah, I would have had it on paper, but think she's stuck. Did she have surgery?
Yeah.
When was that last week?
It was a point in time.
But
I think it was last week.
so yeah, she should be up and running any day now.
Right, up and running.
I mean, I don't really know everything.
No, yeah, so I guess for this first one, I'll probably just do Blackboard questions. Again, you won't have enough time to look up answers. But the big one is that application where you have your data sets. You're going to have to demonstrate that you can actually do this. Do the book. All right. All right.
All right.
So that's time. Let me open up our next. So this was simple. One independent variable. Right? That's what we worked on. Oftentimes we'll have that. And you can design an experiment where you work with that one independent variable. But oftentimes you're going to have more than one. So how do we go about analyzing those data? So what we're going to do is introduce a two-way Anova to start. And this is two independent variables. Both of those variables are categorical in nature. They've got groups. And then you have that one measurement variable, that one dependent variable. And we're interested in figuring out, is there a difference? Do our independent variables affect that dependent variable? Now we're starting with the two-way because we need to introduce this concept of an interaction term. All right. Once we understand that concept, then that same concept applies as we add additional variables to our data set. So we're gonna, like with Anova, we started out with all of our assumptions are met, and then we work through, what happens when we violate our assumptions. We're not necessarily going to do that. We're going to start with the two-way Anova, where all of our assumptions are met, and we're not going to address the violations of our assumptions because we're going to quickly go to 3 and more variables and then address, okay, what happens when we violate assumptions? How do we analyze our data? Because if we have, let's say, 5 or 6 independent variables, how you analyze that is the same as if you had only 2 independent variables. All right, so we're gonna start. You're gonna need these packages. The lattice is for plots, and I'm gonna show you some things on how we can look at some of these interaction plots. This GVLMA, we're not gonna use it for the two-way, but we're gonna use it for our three-way plus. All right, and multi comp, we will likely use it. Also, the data set that we're gonna start off with is cabbages. That's in the mass package. We're also going to use it once we start adding our continuous independent variable as well. We're going to use that because if you look through this presentation and you're like, I don't understand what he was talking about, the cabbages data set is a very popular data set that's used in the help files, other presentations, and so forth. And of course, we've got our own practice problems that we could then supplement with whatever's freely available. All right. So in the cabbages data set, if you looked at your help file, you'll see that what they did was they grouped cabbages and they measured the vitamin C content of those cabbages. All right. Now with the cabbages, they had 2 different cultivars, all right, and then they had 3 different planting dates. I think planting date. There. I believe so. I think that's what it was. Do a quick search for that. So if we go to the help file and just type in cabbages, there it is. I think date was planting date. Yep, 3 planting dates. So cultivar, there's 2 cultivars of it. There's 3 planting dates, and then they measure vitamin C content. They also have head weight, which is when they measured the vitamin C, they recorded how large the head was of that cabbage, with the idea that maybe larger heads are going to have larger vitamin C levels and so forth, and we'll learn how to analyze that. Right? So here's our situation. We've got several experimental treatments at this time. All right? We've got a categorical variable, more than 2 levels, or 2 or more levels, and there's 2 different treatments with that. So they would qualify it for 2 different variables. And then you measured something. That's our continuous variable. And we're interested, is there something affected by those treatments, by that suite of treatments? Now, when we do our display, typically what we're going to do is make means, do a plot of means with standard errors, and we're going to have to break it down based on our levels. But you can't just do a plot of means with the cultivars because you've got this other variable to worry about. And you can't do a plot of date because you have that other variable to worry about. So when you start presenting these data, what you have to really think about is, what's my data structure? What are the differences? Because then that tells me the best way to present our data. So here's one way to look at it. You've got cultivar comparisons where we're comparing cultivar 39 to cultivar 52, all right? And we plotted it for the 3 different planting dates. So we can look at that and say, yeah, it looks like vitamin C levels are different between the cultivars. But if we also kind of do a comparison of the 3 plots, it kind of looks like maybe planting date also has an effect. Maybe planting date causes an increase or a decrease in these in the vitamin C. At least these seem to be higher than all of the rest, right? So how do we approach analyzing? This was a way to make the plot, if you're curious. That's in the presentation, right? The PDF? Oh, it's not posted?
No.
Of course.
That's why you just
Okay.
look at the computer and all of our eyes.
Okay, well, we'll review it because I'm not going to download the PDF and get this going. All right, so here's the idea. We have this interaction plot that will do that partitioning for us. So we don't have to do our subsets and everything else. What we're interested in is this interaction effect, which is basically saying the effect of one variable depends on what our level is in the other variable. All right, so here we might have an effective cultivar, but that effect varies based on when we plant our cabbage. The effect of our planting date may depend on what cultivar we're looking at. All right, so in some cases, let's say Blake's analysis of his crappie. All right, he's got these different lakes. Perhaps the effect of lakes on the parasite community depends on if he's looking at male fish or female fish. That's an interaction effect. All right, and that's what we need to first detect, because if there is an interaction effect, then our post hoc tests, our interpretation becomes much more complicated. All right, so how do we go about producing one of these interaction plots? Well, there's one in the base package, which is called interaction.plot, and there's one in the lattice package called XY plot. Now, with the interaction plot, we have to use the data $ variable format to access it. So one way, instead of doing data $ variable every single time, what you could do is a short way, which is the width function. And the width function basically says, okay, with this data set, go ahead and apply this function, knowing that any variable that's referenced is found in this data frame. Something a little bit simpler, a little bit easier. So what we would do is we're plotting cultivar, date, and then vitamin C. So it's lined up as here's a grouping variable, and we're plotting our Y, that vitamin C. And the function that we're applying is the mean. We want to plot the mean. Now this will add a line, this will connect the means, which makes it look pretty good. And it will automatically kind of do different lines. So solid line, dotted line, dashed line, and automatically add a legend for you, which is nice. All right. Perhaps though we wanted to switch it and we wanted to do date on the X and have 2 different lines for the cultivars. All we have to do is switch the order. Switch the order to do that. With the lattice package, I think it's a little bit easier because we write it as a function, or I'm sorry, as a formula, that up, where we're plotting vitamin C as a function of cultivar, and then we add a grouping variable to say, okay, we're going to plot this relationship, but we're going to do that plot based on our planting date. There's our date, it's cabbages, all right? And then we have to add all this extra stuff. So type A is basically we're plotting points and lines together on the graph. I've adjusted the line weights to make the lines a little bit bigger. The line types, I specified what I wanted in. And line types, we can say is, you know, we could actually use, I believe, the text part of it, or R has a standard order in which we'll plot the lines. So that's kind of what I did. All right, and then you have to mention this auto key to generate the auto key. So there's a few more things we have to do, but in general, the plot comes out is how we like it. This might not be neither of these. This one might be okay for publication quality. This one probably needs a little bit of work. However, you will see some publications use this lattice package to produce their graphs. I can almost pick it up as soon as I see the figures. It's like, yeah, that came from lattice, which is nothing wrong with it, but you just have to know the shortcomings of it. So yeah, XY plot does have difficulty making a decent legend for any of your customized lines or points. All right. So with a two-way ANOVA, our standard ANOVA, it's basically just a standard ANOVA with two independent categorical variables. And the idea is that each of these variables can affect our dependent variable, and the effect may be dependent on the level in the other variables, so that we have this interaction effect. What we're doing mathematically is basically putting together a formula that describes all of our relationships to this dependent variable. So for example, we're doing plant heights and we've got nutrient, fertilizers, and day lengths, right? We're interested in nutrients effect on height and day lengths effect on height. But there's also this possibility that their relationship is modified by this interaction effect, this nutrient times day length effect. The reason I write it this way is because if we use this asterisk, this time symbol in R, R knows exactly how to create the model. R knows, okay, we need to include the interaction effect, and because we have this interaction effect, we also include these main effects. Now, once we have that model, what R will do is generate these sums of squares. So remember, I said the big benefit of ANOVA is the ability to partition out the variance effects. All right, and that's what it's going to do. It's going to say, we've got all this variation in our data. How much of that variation is due to this interaction? How much of the variation is due to day length? How much of the variation is due to nutrients? And then we could use the sums of squares and the degrees of freedoms to generate our F statistics for each of these levels to determine if there is a significant nutrient effect, if there is significant day length effect, if there is a significant interaction effect. Now, also point out that we have the residual. That's our error term. That's all of that unexplained variation that's out there. All right? So, we get, or I should say we get, R will do all of this for us, including calculating some squares and the mean squared terms and the F statistics and everything. It's up to us then to interpret it and figure out what are our post hoc tests, what do we do next, how do we assemble a concise summary that clearly explains what's happening. All right, so what we're going to do, I'm going to stop here because then we'll kind of review it. You'll have the presentation, you'll have the PDF, so we can kind of start getting the cabbages data set in and start looking at it. All right. It's not as scary as it seems. I'll tell you that. All right. So we'll see you on Wednesday.